Camila.
I have to look at the difference in that.
Okay. She was your colleague in UCD, or she was your student?
No, she was a PhD.
The student in UCD?
No, she was a student based in during working centers. She's based in St. Thomas. And she's doing a PhD. She's doing some of the same things I'm talking about in this class.
Yeah, but how did you meet her?
She's a student professor and spent 6 months with me on this project.
In UCD? Yes. So she was a PhD student and you were your supervisor?
So she's still completing her PhD.
Yeah, so under your guidance. Bom, pessoal, boa tarde. A gente está chegando na segunda semana do curso, que é o mais importante, evidentemente. A gente vai começar essa semana, hoje, com a aula do professor Gerald, mas a gente queria conversar com vocês em relação ao trabalho de campo de amanhã e ao final do curso na quinta-feira. Então, o trabalho de campo amanhã, a gente vai ter uma visita de uma sujeito que foi estudante de PhD, doutoral, e foi bolsista na UCD, o professor Gerald, Dublin. E essa pessoa ela vai fazer uma introdução do trabalho dela, ela está sediada em Santos, e ela foi estudante de PhD em São Carlos. Então, ela vai fazer uma introdução à aula do campo da manhã, aqui com vocês, vai apresentar o que ela fez, o objeto da pesquisa dele, e a continuação vocês vão fazer o campo com o professor Gerald, pretendo acompanhar a extensão. O campo vai ser muito próximo daqui, o bairro que fica logo depois do CEPAM, o antigo CEPAM, não sei se vocês conhecem, atualmente é a sede do Centro de Estudos da Metrópole do Centro. É a sede do Centro de Estudos da Metrópole e tem a grade da USP tem uma passagem de pedestre ali, não passa carro. Então tem um bairro residencial que tem uma mistura interessante de vegetação, prédios altos e casas residenciais de baixa altura, depois no máximo 2 andares, e o professor escolheu isso como o objeto do campo que vocês vão fazer amanhã. A continuação, amanhã termina esse campo. Na quinta-feira é o último dia do curso. Então, como a gente tinha falado no início do curso, essa avaliação, a sugestão nossa é que vocês fizessem em duplas. Então, e a apresentação fosse em inglês. I'm just explaining what we more or less we talked at the beginning of the course. O professor ele sugere que vocês, I think it's better you explain what you intend for them to explain in English. Yeah. There is a doubt I translate because I think that
yeah, of course. But today and Tuesday, I'm going to talk more specifically about the urban climate effect, specifically on things like the urban heat island and how buildings affect local climates. So I'm going to talk for about an hour, then we're going to take a break as I transfer a lot of the data that I need to put onto the machine, so I can just show you what this particular piece of software I'm going to use is capable of. So today, the focus will be on using this particular package called UMAP, which is a plugin into Qgis. And in particular, as I've said before, the most important variable that determines local climates, microclimates, is sunshine. So So I'm going to use this package called Solweg, and I'm going to use some data that exists for Sao Paulo. This data consists of the footprints of the buildings and the heights of the buildings. And I'll show you how that data can be used to do some very simple things about plotting sunshine patterns, and even to estimate what we call the mean radiant temperature. So that's today. Now, what I've been talking about in the past, and what I'll talk about today, is what really characterizes climates of cities is the sheer variety of climates over very short distances. So that's what makes them different. And part of the reason for those extreme variations over very short distances is because of the types of buildings that we put up and how we lay them out. In other words, how close or far apart they are, what types of materials we use, and how those buildings are actually employed by using on a day-to-day basis. So that's what I'm going to talk about today. From last week and today, all I've been talking about is how cities affect climate. They do so at the scale of a building, they do so at the scale of the spaces between buildings, they do so at the scale of cities, they do so at the scale of regions, they do so at the scale of the entire planet. In other words, cities are partly responsible for changing the climate of the planet. And of course, that means that cities are also subject to all of those changes when they happen to the city. So that's what I've been doing up to this point. Tomorrow, we're going to do a small field trip. To a place very close to the campus that has a variety of building types, different heights, different ages. So we can just talk about all those things I've been talking about in practice. Before we have the field trip, we'll meet here and talk for about an hour. I've asked a colleague of mine to come in to talk about a project that she's working on in Santos. And the reason Camilla's going to speak is because she's using UMF and Solweg, and she's done an urban heat island study, and I know that it makes good links to the work that you're doing, the work that you're doing, and the work that Luciana's done. So I think it's a good opportunity for us to talk in general about the application of these ideas to a particular place, how you might actually use Solweg to urban design. So that's Wednesday. We're going to meet here for about an hour. Then we're going to do a field trip. I think the field trip will only last about an hour and a half. And then we might either discuss on the way back or hear what the results of that field trip are. For myself, whenever I do one of these field trips, I do these field trips in Dublin with my students. I do them in London with a colleague of mine. I always take a notebook with me so I can write down ideas, things that I see connections between. As I said to you before, what we're trained to do now is to use scientific instruments to measure solar radiation, to measure temperature, to measure pollution. But in fact, your body is a perfect integrator. You can feel wind, you can feel temperature, you can smell pollution mostly, and you can hear noise. So in other words, your body is quite capable of integrating all these different impacts. You can't give precise numbers to it, that's why we have instruments. Nevertheless, you're quite capable of converting your experience on the field trip back into meteorological outcomes. So on Thursday, when we meet here, the first hour I will summarize what I think the course is about. And in particular, I'll try to put cities and climate, associated cities, into the context of global climate change. So that'll be the first hour. And from that point onwards, I thought a good way of having you assess what this course has meant to you, your understanding, is for people to give short presentations. Those presentations might have just 10 slides. The first slide would just be your name, and tell us what you want to talk about. Now, because I know it's a bit of a big ask you to speak in English so that I can understand, you can either do it singly or in pairs. You could base it upon work that you're already doing, such as your work in Aula, or you could do it on how you feel the work that you're doing connects with something that we did in this course. So if you could, for example, discuss the course itself and how you're going to integrate it into your own understanding of cities, or you could take your own work that you've already done and simply link it together with the work in this class. 10 slides. Huh?
1 minute each.
About 1 minute each. Now I'll be here on Thursday morning at about 10 o'clock in the morning. So if you had your slides and you wanted to show them to me, I'll be sitting in the professor's office just down the way here. So if you want to come in to see me and show me the slides that you're going to do, I'll be happy to go through those slides with you before you present. Does that seem fair to people? Is that okay? As I say, if you feel uncomfortable about making the presentation in English, if you put together your slides, if you come and talk to me beforehand, I'll be there from 10 o'clock in the morning until we teach class. I can go through the slides with you and tell you how I would arrange them to make the best possible presentation. Is that okay with everybody? Now, we've got complete flexibility. In other words, you might be already working on a project and you see some things that I talk about that can be linked into that. Or maybe that you've already done some piece of work that you'd like to share with people on the urban climate or the urban effect. That's fine. Or maybe that you want to take, say, something like, say, for example, the field trip we do, and to talk about how what you saw in the field trip connected to some of the ideas that I spoke about in the past. In other words, you've got complete flexibility. All I ask is that you show some engagement, to show that the topic that you've chosen fits with some of the ideas that I spoke about in the past. 10 slides. The first slide is your name and title. The last slide is your conclusion. So you just need to write that slide. For me, as you see, I love photographs because I think photographs tell stories. So you can tell lots of things about one photograph. I can talk about what's in that photograph. That fills up your time very, very easily. So the way I normally do a lecture is I figure out how long each slide is going to take me to go through. I have pictures, but then I usually write down some notes. Now I've been doing this for about 35 years. But I can tell you every time I do a conference, if I only have 15 minutes or if I have 10 minutes, I will spend a couple of hours going over and over the presentation so that I'm fully aware of how much time I have to deliver the information. Okay? That's reasonable? Okay. Okay, everyone?
Yeah, perfect. Do you think you will need the instrument that you used the other day for tomorrow?
Yes, it'd be good if we had those instruments. The instruments that Ronaldo was speaking about are those instruments that measure the radiant temperature, the air temperature, the wind velocity, and the humidity. Yeah.
Dúvidas? Alguém certo?
Eu queria saber o que você explicaria depois de UM.
The humectas Sol, S-O-L-W-E.
Peraí, devagar.
S-O-L-W-E-I-G.
I will show you when we do it. So I'm going to speak for about an hour.
Okay.
Then I'm going to take a break because, well, I'm not sure how good these machines are at processing a lot of data. So I just need to copy some of the data I was playing with on this computer here onto these machines here to see what can be done. We should be able to map things, but when it does processing, I figured these machines might be too slow to do some of the processing within the time frame of the class. Nevertheless, I'll be able to show you what this thing is capable of, and if you have a day rather than an hour, then these machines can do it, they'll just take a long time.
Yeah. I'm going to collect the things to prepare for you as well.
Okay.
Come back. Pessoal, desculpe, todo mundo está consciente de que está tarde às 6.
So I'm trying to cover a lot of things in this class associated with how cities affect the environment. And I've emphasized certain terms. One thing I've always emphasized is the importance of scale. Okay, I cannot emphasize how important scale is from the perspective of examining the urban environment, and especially the climate. Scale is absolutely critical because it determines every single thing that happens. Now, what I'm going to talk today about is how cities affect the climate. So far, I've done it in a very, very general sense. I've spoken about form. And form, I've said, has got three aspects to it. One is land cover. No, that's land cover, not land use. That means, generally speaking, when we talk about land cover in a city, we talk about landscape that's impermeable, paved, and landscape that's permeable, which is usually vegetated. And the impermeable land cover might be buildings, but it might also be road, might be paving, might be car parks. The permeable land cover, the green land cover, might be parks, but also might be quite subtle, it might be trees. In other words, trees provide an opportunity for the atmosphere to interact with the ground by the root system. So that's land cover. What distinguishes the urban environment is the fabric. In other words, if I say the land cover is impermeable, then the fabric is all the materials that are used to make that impermeable cover. This is the concrete, the asphalt, the glass, the steel, everything that makes the land cover basically impermeable. Fabric is manufactured in a city. And manufactured materials are hard and they're dense. That means they have very, very consistent properties. But something we also mentioned, that what makes a city different from the surrounding natural area is that the city, generally speaking, is consistent in terms of its properties. The natural environment changes with the seasons. When it rains, when it's dry, when the vegetation grows, when the vegetation dies, it changes naturally. The city is designed to be consistent. That's what distinguishes it. And there's a geometry. This is the heights of the buildings, the dimensions of the buildings, the spacing between the buildings. These are all the things that make the city a very, very rough surface, a very, very confused surface. As shown here, this is I don't show you the building here. This is a classic example of a very, very badly designed building. It's a very, very tall building. It looks like a big slab. It's a very, very tall building, and all the buildings around it are very, very low. So not surprisingly, when the wind strikes this building, the wind runs down the front of it and causes all sorts of wind problems in space. So these two people are trying to hang on for dear life to the poles simply because the wind is blowing them over. That's geometry. So they're the things now that are associated with the physical imposition of landscape. By physical, I mean that we have built these things, we've put them in place. Even if I left, the city would still be in place. If this city were to be evacuated, you'd still have the land cover, the impermeable, you'd still have the fabric, and you'd still have the geometry. It would take a long time before the vegetation took it back over again. So that's form. This is about land use. This is about function. This is about how urban spaces are used. And I divide it very, very simply into residential, said commercial. I said industrial. I said transportation.
I'm sorry, before when you were talking about form, you said that these three are physical what?
Aspects of physical geography.
Okay.
In the same way that if you went out to look at a valley that's cut by a river, you would describe its physical geography in terms of the width of the river, the width of the floodbank, the height of the sides of the valleys. In other words, you describe it in terms of how it's made up. You might take a soil sample. You talk about the vegetation. You talk about basic physical geography. Typically in geography, we do something very silly. We say, okay, everybody over here is human geography. And everybody over here is physical geography. This is complete junk. Right? Makes no sense at all. Because I am obviously a living creature also. And that means that I adapted, changed, modified the physical environment. The two things are in fact overlapping. But for the sake of identifying causes, I'm describing this as what we would normally call the physical geography of the landscape.
Yes, because I had wrote physical landscape, but I was confused if you said physical landscape, what it was. Thank you.
Yes. Whereas the function is essentially how we occupy that landscape. Some of the geometry is occupied by residences. Some of it's occupied by institutions. Some of it's occupied by commercial. Some of it's occupied by industrial. The other one that's down here is transport. And typically we refer to this as the human geography of the city, how the city is actually occupied and employed. But the one thing I've been saying repeatedly is that these two things are completely connected. The type of form, the type of geometry depends on its function. I build an institution. I build a house. I build a building that's going to be used for industry. Now, what really distinguishes these is that the function we often look for a measure. One of the measures I spoke about in this class is that the functions of the city, things that sustain it. Things that sustain it is a constant throughflow of materials which generate wastes. So a lot of the inputs for this, the creation of fabric, the manufacturing of concrete, the manufacturing of steel, of glass, the assembly of it, the creation of geometry, that's the inputs that give rise to the actual land cover. The land cover consists of all the inputs of mining, taking all the stuff out of the ground, the gravel, the water. Then there's all the manufacturing process, the heating, to generate the fabric, to make the glass, to make the concrete, to make the steel. Then all this stuff arrives in the city. You can see it all over Sao Paulo. It has to be all assembled, put together. And that's how I get the city itself. So we refer to this, if you remember, as embodied. This was the energy that was actually hiding when you put together the city.
Is it written embodied energy?
Energy.
And of it is stored.
You get inputs, some of them get stored in the city. That's how you get the physical landscape. Storage.
Storage, thank you. I did not.
And there's also outputs. Okay, in, out. This is a diagram I would have used before. Just turn on the lights for clarifying these matters. Oh, no, you're fine. So that's why I call it embodied. Hiding the body. Okay? But then the city also needs all these inputs just to sustain itself. A building like this requires energy all the time. It requires water all the time. Commercial enterprises are very, very similar to this type of building. It requires energy, water, materials, just to keep on going. It requires paper, it requires electricity. Industry requires all this just to manufacture. Industry includes the generation of energy. So, for example, if there's a big power station here, it might bring in coal, it might bring in oil, it might bring in gas. And then, of course, there's the energy associated with transport. So this is what I regard as the energy that's required to sustain the city. And of course, the big question is whether, in fact, constructing the types of cities that we do, having them function the way they do, whether in fact they are actually truly sustainable on a planetary basis. Sustain here means simply to keep going, the same way that I have to eat food to sustain myself. But sustainability at a planetary scale generally means, can I continue to do this forever? The answer is no. That's an easy answer. So the only question is, how do we change the form of the function to make it more sustainable? So land cover represents the actual physical, and land use represents how the city is actually organized. So for example, this might be residential on the outside. It might be commercial in the city centre, like here. And in between there might be, I don't know, warehouses. My point, however, is that you can generate a land use map of the city. That land use map, when we say about occupation, is closely connected to the land cover. Depending on the land use, that's how you get the need for transportation in and out of the city, transportation between the city and the wider world. That's the energy that's required to sustain it. So, typically in many Western cities, less so it seems to me maybe in Sao Paulo. Okay, that's the typical sort of description of the city. Where we place our homes, where we have work, and then the transport to get back and forth. So when people talk about cities, they say, okay, can I change the nature of the functions? Can I make the transport more sustainable? That means from the car to a bus, to a cycle, walk, for example. Can I make the home more sustainable? That might be PV cells, photovoltaics, might be improved fabric. For example, so that's what people talk about when they talk about sustainability. And here you might say, for example, can we have different work practices? And then some people say, look, we're thinking about this a lot. What we really need to do is get rid of this part altogether, mostly by sticking the home and the work together. So some people say, you can solve all these problems if, in fact, I can work from home. So therefore, need for transport. But you can see then, when people are talking about reorganizing cities, rethinking about cities to accomplish certain goals. What I've been doing in this class is moving back and forth along the scales. So, for example, I talked about air quality. Essentially, it was about trying to figure out how to sort out transportation, how to sort out emissions from work, how to sort out emissions from home. When I talked about human comfort, it was about what types of homes you wanted, and how much energy you were prepared to put into those homes to attain it, and how it might be achieved. For example, is the best to simply shut off the house from everything else, then put in any energy into the system that needs to protect it? Or is in fact the best solution to allow air to flow through the system, so it's passively ventilated? These are the big questions. Okay, so that's the various bits and pieces I've been trying to put together. Now, what I want to do today is I'm going to tell you specifically about the climate effect. In other words, the consequence of talking about the city and urban form and the function is it produces a very, very specific climate. I know that many of you are studying it at different scales, so I'm going to introduce more formally how cities affect the climate. Two terms here, weather and climate. They're often used interchangeably. And the difference is that weather represents the instance, the weather of today, the weather of now. Whereas climate represents the normal patterns of weather. So I can talk about this why, for example, people often get confused when we talk about projections of climate change versus predictions of weather. The two different things. Because what the climate has got to do is the ordinary average pattern of weather throughout the year. So it's obvious this time of year, Sao Paulo actually has quite a cool climate for many days because of the passage of frontal systems through the city. And they're bringing cold air and implication, lots of cloud. But that later in the year, as you move out of as you move out of winter towards spring, what happens is the position of the sun relative to the earth changes, and Sao Paulo's climate also changes. And that happens on a regular basis, associated with the movement of the earth and the sun together, which causes the climate. But on any given day, you get weather. So when people talk about how the urban system affects, we have to think about how it affects weather on a day-to-day basis and how it affects climate. Climate being the average weather that you experience. Now, we normally talk about the elements of weather and climate in terms of each of the parameters, be it wind, temperature, sunshine, cloud, etc. What you see is that the effect of the city is modulated. It has bigger effects on some things than on other things, and that effect is largely determined by scale. That's why when you talk about how to influence the climate of the city, you have to talk about scale all the time. So what's climate change? Well, climate change simply says that the statistics of weather will change. The expectation is that the statistics of weather on the globe will give rise to warmer climates in the future. And the reason for this, we'll talk about this the next day, on Thursday, is simply that one of the products of creating form of functions is the generation of a very peculiar gas called carbon dioxide, CO2. So So one of the most energy-intensive production processes that uses up and generates an enormous amount of CO2 is the manufacture of concrete. So if you want to find the biggest sources of carbon dioxide on the planet, it's almost always associated with the manufacture of concrete. And then, of course, all the cars, all the vehicles, either directly or indirectly, run off fossilized fuels. That means that all of transportation is fundamentally associated with the generation of CO2. The same thing will be true of most of the energy used inside buildings. In Brazil, you get a fair amount of your energy from hydroelectric schemes. Hydroelectricity is carbon neutral, except, of course, in building, you need an enormous amount of concrete to build a dam. So that means that it has embodied energy simply because it built a dam. The other alternative source of zero carbon fuel is nuclear energy. So nuclear energy does not generate fossil fuels, does not generate carbon dioxide, and neither does photovoltaic cells and renewable energy sources. But for the most part, anything associated with transport on this planet and the creation of fabric almost invariably involves CO2. CO2 is accumulating rapidly in the atmosphere and has a very, very peculiar property. And we've known about it for more than 100 years. So although people talk about climate change now, in fact, it was well known back in the 19th century that increasing the amount of carbon dioxide in the atmosphere would cause the planet to warm. That's what climate change is associated with. So when people talk about urban climate, it's about planning for now and the weather now, planning for the climate now, and for planning for the climate in the future. So, just a recap as to how the atmosphere responds to the surface. If I take a typical day which is sunny and there's very little wind. Now, this is important because what wind does is it mixes the atmosphere. So if I have a park and there's a wind, the effects of the park will be blown into the surrounding terrain, and the effects of the surrounding terrain will be blown into the park. So wind is a great mixer. If you have a day which is sunny and it's calm, then you'll start to see the atmosphere respond to the surface that sits on. If you walk around South Aula late in the afternoon, you can often get the smell of all the air coming in from the ocean. I don't know about people felt that. There's certain streets in the city, even walking around last Sunday, it was a nice sunny day, by about 2 o'clock in the afternoon, you could feel the air coming off the ocean. So there's an example of wind. And wind is taking the properties of the ocean, like a natural air conditioning system, and it's transporting it into the city centre. So wind is a very, very important mixer. Typically, if I get a sunny day and there's a wind, what happens is the atmosphere starts to respond to the surface over which it sits. And remember, the atmosphere is, relatively speaking, it responds to the surface. It does not respond to the sunshine. Sunshine passes through the atmosphere, it's absorbed at the surface, then the surface starts to churn itself, mix it up, and all the properties of the surface get mixed into the overlying air. So that might be a typical field in Ireland. Grass, you can see in the background there, they're growing some what they call rapeseed, yellow. What's happening over the course of the day, late afternoon, is that the effects of the surface and the mixed upwards, you see how all the clouds have a flat bottom on them? So this is the layer into which all the layers get mixed. Okay? That's what we refer to as the surface layer. If I make any measurements inside the surface layer, I can relate them directly back to the surface on which it's sitting. Above that layer, you say the atmosphere is mixed. So the atmosphere up here contains some of the surface below, but contains some of the atmosphere that was not associated with that surface. But you can see the entire depth of the atmosphere is about 1 to 2 kilometers. So that atmosphere will be mixed and connected to the surface below. If that surface is moist, the atmosphere above it will be moist. If that surface is dry, the surface above it will be dry. If that surface is polluted, then that atmosphere above it will become polluted. So, this is how we normally divide the atmosphere. Two parts, the surface layer and the mixed layer, and put them together, and they form what's known as a boundary layer. So the planetary boundary layer is usually about 1 to 2 kilometers thick during the daytime. And the thing is that if I put a measurement or an instrument inside that, over the course of the day, I can see the effects of the underlying surface. Sunshine arrives, warms up the substrate, warms up the surface cools at night, warms up again, cools down again. And I'll feel all that within that layer there. Above it is what's known as the free atmosphere. And typically, when weather forecasters start to do their forecasting, that's where they focus their attention. So all the original forecasts really did not deal with this. They tried to figure out what was happening in the free atmosphere, where the big atmospheric controls were operating. And they didn't really focus on this layer here at all. So if that's daytime, this is what's happened at nighttime. Nighttime, the energy source is gone. Everything starts to cool down. Suddenly, the mixing layer gets radically reduced. The surface layer gets very, very thin, and the air above it starts to reduce. Now I have to go maybe half a kilometer, and all of a sudden I'm in the free atmosphere. So you can think about this boundary layer like a little cushion of air, thick during the daytime, or at nighttime. Thick, thick, narrow. And that cycle is driven by energy from the sun. Sometimes you'll find that that surface layer cools sufficiently that it'll actually pass the saturation point and get the formation of a cloud at the ground. It tends to be formed in the lowest layers. That's of course what we refer to as a radiation fog. Fog is the same as cloud. Okay? There's no difference at all. Fog is just a cloud at the ground. So radiation fog occurs on these nights here when the ground cools, the air cushion gets very, very thin. So how does the surface interact with the atmosphere? Well, it interacts through turbulence. And the easiest way to think about this is if I set a balloon in the ground, what I find is generally speaking the wind will get stronger and stronger and stronger with height away from the ground. So if I was to measure wind speed against height, I'd find that the wind at the ground would be zero. Because at the ground, the air is fully stopped. The wind speed will increase with height, and eventually will start to stabilize. So here I am now about 100 meters. So much of the momentum of the atmosphere, the movement of the atmosphere, is pulled out of the lowest layer. And then that lowest layer, we have our pockets of air that swap their position. So when they swap their position, they bring down fast-moving air for the ground, bring down slower-moving air, push upwards. And it's this mixing that carries up air temperature and humidity. So when the atmosphere is functioning, it's constantly churning itself, and that's how the surface layer develops its properties. So during the daytime, when it starts to get warmer and warmer and warmer, what you start to see is the atmosphere gets more and more turbulent. Big pockets of air go away from the ground, big pockets of air come back to the ground. And that's how it mixes itself up. So if I measure the wind speed, so this is a weather station in Ireland. There's 11 o'clock, noon, 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock. The wind is never constant. It's jumping up and down. Now, why is it doing that? What you're experiencing are those pockets of air, very fast ones coming down to the ground. You feel a big push, that's a gust. Then all of a sudden it goes calm again. That's a lull. So this rapid change in air properties is associated with turbulence in the atmosphere. Now, natural surfaces, the amount of churning that goes up on the atmosphere depends on the surface temperature. It also depends on how rough it is. So for example, water is a very, very smooth surface, which is why if you have a hurricane coming in from the ocean, it is the buildings which is adjacent to the water that are going to get the biggest impact. As soon as the hurricane moves over the land is very rough and starts to slow down the atmosphere. But the first occasion that the air meets the land, straight off the ocean is completely smooth. That's where the wind speed is strongest. Short grass, again, is quite smooth. Longer grass tends to be rougher, and forests are rougher still. So forest is a rough surface. Okay, there's our description of the natural environment. Now all I have to do is think about what cities might do. And here's my description as to how the atmosphere, or how the energy gets exchanged. We talked about this beforehand. Typically, energy comes in from the sun, we call that K down. Meets the surface, a portion of it is absorbed, a portion of it is reflected. That's why I call it KO. This is radiation from the sun. All of the surfaces also have a temperature. The surface radiates energy outwards, but also receives energy back from the atmosphere. So K down, KO, L down, L up, representing all the radiation streams. At night time, no more sunshine. What happens is the ground cools, mostly because it gives away more radiation and gets back to the atmosphere. So this is the typical pattern of the course of the day. So I've now talked about how the system responds to energy and how it responds to wind. We say that the amount of energy from radiation, KL, is spent in either heating up the air, central heat, in evaporating water from the surface, or in storing heat in the ground. So during the daytime, energy from the sun is used to heat up the air. Temperature of the atmosphere goes up. It's used to evaporate water, if in fact the grass is green and there's lots of moisture available. And it's used to warm up the ground, the substrate. At night time, what happens is the atmosphere cools, the heat is sent back to the surface. Condensation occurs as water vapor is sent back to the surface, and the substrate is cooled, the energy is taken back out of it. So on a typical day, what you see happening is, in the morning hours, very little energy available from the sun, the ground is quite cool, any energy is coming in is going into the substrate. The day goes on, the ground gets warmer. As it gets warmer, you start to get little bits of turbulence happening. More and more crustiness, more and more lows. What happens is the energy gets transferred into the overlying atmosphere, you start to get evaporation occurring. That happens throughout the day until about 4 o'clock, 5 o'clock in the evening. Then all of a sudden, the sun starts to go down, the ground starts to cool, and all the systems start to reverse. So the energy is going from the atmosphere back to the ground, water vapor is going back to the ground, you get the formation of dew at the ground, and then energy is taken back out of storage. So there's your typical day. Okay. Some of these ideas that we mentioned before. So what's the effect of a city? I think this is a great diagram. Though some of my architecture friends say it's difficult to read. It's got 3 scales to it. They're all cross-sections. This first cross-section is the entire city. Every one of those blocks there represents an individual building. What we have here is the air is coming in from the countryside. There's the planetary bounded air. There's its depth. There's the surface layer. Okay, so that's the layer in which all the exchanges are completely linked to the surface layer. This is the layer where there's mixing going on, and this is the layer of the free atmosphere. So as the air comes in off the countryside, or off the natural environment, look what happens to it. there suddenly meets a new surface, the city, and it starts to interact. This surface is quite rough, which means it's generating a lot of turbulence, and it also tends to be quite warm. That means that all the air that's coming off that ground is transferring the effects of the city into the overlying area. So at the point that it starts to meet the new surface, a new boundary layer develops. That boundary layer is the city's boundary. In other words, anything I measure inside that plume there, I can identify as belonging to the city below. Because the air is coming in this direction, notice that it gets thicker and thicker until eventually I meet the limit of the mixing layer and extends downward. Here's the far side of the city. Now it encounters, again, natural surface, and new boundary area develops. Anything I measure inside this area here can be linked to that natural environment. So that plume there represents the urban effect. And it will go for kilometers downwind. So anything that gets mixed into the atmosphere here, all the pollutants, all the gases, all the particulates, they'll all get transported downwind in the urban plume. In fact, they will go thousands upon thousands of miles sometimes before they fall back out again. So that means each individual city will develop its own plume that will wash out all the materials. So if I was in an aeroplane and I took a flight or a helicopter and I flew through here, I'd be able to measure nice and cool, clean, the area from the water area below. I enter the UEL, suddenly the atmosphere gets a little bit cloudier, a little bit dirtier, a little bit warmer. And the reason is because it has the effect of the city below. All the way through the plume. And sometimes, if you've flown into Sao Paulo or to any big city, you'll know this. Because when you're flying in the plane, you're looking down the city below, it's almost like a veil over the city. The veil, on a day like today at Sao Paulo, you'd see it looks a little bit cloudy. And the plane is nice and smooth. And then as the plane starts to land, as it comes into the airport, all of a sudden, it starts to get bumpy. What your plane is feeling are all those pockets of air rising and sinking within the mixed layer. So the plane starts to bump about as you enter into the urban plume and eventually you land. So that is the urban effect on a grand scale. All the stuff associated with the city into the atmosphere to the extent. The city itself is made up of different neighborhoods. And each neighborhood might be residential, might be commercial. They all have their own distinct effects. So this is what they refer to as a local scale. It's about 1 to 2 kilometers in extent. So Sao Paulo is probably about 1,000 square kilometers or thereabouts. So a neighborhood might be just 1 or 2 square kilometers within it. And each of those neighborhoods sends its own distinct signal in the atmosphere. So here's our surface layer. And you can see the surface layer extends maybe about what? 10 times the height of the buildings. Inside the surface layer, we have a very, very rough sublayer. This is where the atmosphere is extremely confused. The reason it's confused is because of all the individual obstacles here that the air has to go around. And because it has to go around them, that means that each of these obstacles generate eddies. This is the same, for example, if you go down to the middle of Sao Paulo and there's a breeze, if you stand in a corner, you can often feel the eddy come around the corner, and you can feel it on your body. Sometimes you'll see rubbish on the ground go round and round in circles. These are the eddies that are generated within this layer. But then I can go even smaller. So if that's an entire neighborhood, somewhere you have trees, you have different types of buildings. Here we have now a microscale, a single city street. So there's my individual buildings, there's the roughness there, and this is my traffic. So here we are. If I'm standing here outside this building here, I'm experiencing micro. If I start walking around the campus, on a distinctive local scale. To get to the city scale, I have to account for all the local scales that make up all the city that make up, say, South Pole. Now, from the point of view of trying to design a city for humans, that's the scale, the micro scale. You might try to create a local scale where there are lots of different types of microclimates that you feel comfortable. But ultimately, that's the scale which you design. This is the scale which you plan. This is where you make the big decisions about where do I put the different types of land uses, how do I have the different types of land. Once I've made those big decisions, and I have to actually divide it out and identify parts of the land and create nice spaces, then I get down to the decision about everything that happens in between the buildings, which is the spaces that we occupy. Yeah. I think it's a great diagram because it summarizes everything associated with the urban climate. So what does that mean? Well, you remember before I talked about the wind, and I talked about how it mixes itself up, and I said that the nature of the wind depends to some extent on the roughness of the surface. But here's the thing. In an urban area, the surface consists of all the buildings. So that means that the effect of the buildings is actually to push the exchange of momentum in the atmosphere well above our heads. And in between the buildings, what we get is pure roughness. We don't get the mean airflow, we get the airflow that's been churned up by the individual buildings. So here's often a measure that people use, it's called the roughness length. So over something like open sea, the roughness length is very low. Over open land, you can see it's a bit higher. Here's the suburbs, here's the city centre. The city centres are especially rough. That means that the mean airflow in a city cannot be found in the individual streets. It's found up near the top of the buildings. In between the individual buildings themselves, the airflow is completely turbulent. Now, this has implications for air quality control. It also has implications, for example, if you said to me, I'm going to put up a wind tower on my building, and that wind tower is going to generate energy. Well, I can tell you that if you put your wind tower in between the buildings, it will generate no energy at all. And then, in fact, if you want to generate any energy from the wind turbine, you have to get high above the buildings. So that means in South Hall, you'd have to have a wind tower that's probably about 130, 140, 150 meters tall just to access the wind. Once you get closer and closer to the city surface, the atmosphere gets extremely turbulent. And turbulence destroys wind power. So this is the level which we occupy. So we don't find ourselves getting the mean airflow, we find ourselves getting the turbulent airflow. And for this reason, getting information from your local weather station about the wind is of very little value for knowing what's happening in individual streets. Because what happens in individual streets depends completely on the geometry. So here's some examples. A lot of the work that people have done on wind inside cities is based upon wind tunnels in the past, and now it's based upon computer modeling. So here's a wind tunnel. This is a classic sort of setup, where you have a tall building that's a big slab, and there's a shorter building in front of it. So what happens? Well, first of all, the air gets displaced around the shorter building. The fast-moving air hits this side of the building here, and then runs down the face of it, and now it's blocked on this side of this building here. So you've generated a big vortex within here. Think about what happens if there's cars moving down the street, all of them generating pollutants. The pollutants go up one side of the building, go across, and back down again, stay in place. They don't. Here's a single building all by itself. In other words, it might be very, very small buildings around it, and then one big building by itself. This, by the way, is the reason why those people were hanging on the pole in the first picture. Here's the fast-moving wind. This is where it gets to stagnation point. The fast-moving wind there creates pressure against the building. Because it creates pressure against the building, the air flows down the front of the building and around the sides. So on this face of the building, the very, very fast-moving air is now walking down the ground, where it creates these eddies. It goes around the edges of the building, and then creates new eddies behind here. In other words, that particular type of building disturbs the airflow thoroughly. If you look around buildings in Sao Paulo, I don't think you get very strong winds here, but you see a lot of the buildings are slab-like. Now, if they are facing the wind on a windy day, they're not comfortable places to be built. Sometimes you'll see that the designers, once they built the building, realized they'd made a mistake, so what they put down here is vegetation, lots and lots of trees. And the reason for that is to provide a cushion to protect all the people on the ground from all the air that's coming out the front of the building. Some of these buildings, when they started constructing them in North America, they had very little vegetation. And whenever you open the door at the bottom, all the air that suddenly, especially if there was two doors on it, as soon as you open the two doors, basically the air will rush out of the building or rush into the building and cause all the windows to pop out. So very tall buildings have immense impacts. Here's a simple way of determining whether, in fact, the nature of the wind. All of these winds are perpendicular to these two buildings. So here's two buildings. They're so far apart, they're aerodynamically separated. Here's the airflow of one building, creating an eddy in the lead, an eddy at the front. Then the air returns back to its normal. There's another building with the same effects. So these are independent. This might be buildings out in the countryside or in big central areas. Start the building, bring the buildings closer and closer. First of all, we get interference. So now you can see that the downwash of this building here is affected by the recirculation of that building here. The result is extreme chaos. This is very, very good, by the way, if you want to get rid of pollutants. If there's lots of cars on the road here, this is the effects of mixing them up. Here's what you don't want. Here the buildings are so close to each other that the air above the street jumps over the street, transfers momentum to the air in the street, and you get the formation of these recirculating eddies. So these are the ones that are associated with worst air quality, because these are the ones where the air below the street is isolated from what's happening above.
There's some way to calculate the distance between both buildings to make the air circulate in between them.
Well, generally speaking, the simplest measure is, well, there are two ways. The geometry affect airflow. One is the orientation of the street. So if the street is oriented along the airflow path, the airflow of the street. If it's oriented and across it, then it blocks the airflow. So that's geometry. Orientation. Here's the other one. The height of the buildings and the width of the street. Generally speaking, if the ratio of height to width is about 1, then you get this type of flow. If the height to width ratio is greater than 1, then you get scaling flow. And if it gets way beyond, say, 3 or 4, you get ice flow. But it depends completely on the ranges. It also depends, here it's very simple, all buildings are exactly the same height. But whenever you get buildings of different heights, you get different types of wind patterns. I didn't talk about this, but in Hong Kong, where the buildings are extremely tall and extremely close together, they have a bit of a problem. The problem is that, where you see the pictures of Hong Kong, the space between the buildings is very, very small. But there's an awful lot of cars coming down the street. That means the air quality in the streets is very, very poor. Now, if you look at a map of Hong Kong, it is adjacent to the ocean. So its natural ventilation system would be in the afternoon, just like Sao Paulo. All the air will come into the ocean and clean up the streets. Bring a nice fresh air from the ocean be cooler, be more humid, you feel more comfortable. But they built Hong Kong so densely that the air from the ocean cannot go into the streets because it's blocked by our buildings. The consequence is they essentially cannot clean out the streets. Now, recently they developed a plan for Hong Kong, which is called a ventilation strategy. They're actually planning on removing very, very tall buildings inside Hong Kong, not individually, but surgically, to ensure that air can move along the streets. So identifying buildings that they can remove, so the air from the ocean can move in along the streets to provide ventilation. So there's an example of planning at a city scale to try and manage these types of things. Okay, one aspect is geometry, how it affects the wind. The other thing is, of course, how I manage the type of fabric. We spoke about the land cover. Generally speaking, if a surface is green, the energy will be used preferentially for evaporation rather than heating the overall. If a surface is completely paved, most energy will be used for heating the air. So without doing any experimentation at all, I can tell you that if I was to measure air temperature, it will be cooler over this surface here on any given day than it will be over any surface that you see here. So big effect we know of cities on the overlying climate. I mentioned wind, the other is on air temperature and surface temperature. So there's my fabric. This is a classic example. Asphalt, black, on a nice warm day, no water for evaporation. These surfaces get extraordinarily hot. Put your hand down and try and touch it. Some of these surfaces are hot enough that if you give it a few minutes, you can fry an egg. It's hot. They would regularly measure temperatures here on these surfaces of 60 and 80 degrees Celsius. In fact, I think this picture comes from Arizona, where they tell you, do not let your dog walk on these because poor old dogs, you know, the pads have got no insulation at all. So that means they tell you that stay on these types of paving if you're doing out your creatures. And this is a typical rooftop surface in North America. Dark rooftop surfaces. By the way, pretty good in wintertime, right? Because dark surface absorbs any radiation from the sun. In fact, if there's snow on these surfaces, and the snow is sufficiently thin, the sunshine will penetrate the snow, the surface of the roof will warm up, and the snow will melt. But during the summertime, these are extremely problematic because they get extremely hot. The real issue for these types of buildings is often that the rooftops are very poorly insulated. So that means the real issue is to try and provide sufficient insulation for the rooftop. Nevertheless, you can see that dark roofs, which are dry, are going to get extremely hot. It's going to heat up the overlying air, but they're also going to heat up the roof below. Here's my 3D geometry. This is New York Street. New York has tall buildings. But New York's actually, certainly Manhattan, which we always take to be extremely high-rise, is very well designed. In New York City, from the center of the street, I should be able to see about 67 degrees of sky below me. The reason for this was the planning law that was instituted in 1918. So you might say, why did they have such a planning law in 1918? But they had it so that each of the individual buildings could get access to daylight. Because if you go back a century, the cost for lighting buildings was extremely high. So what they did was, they put controls, once they had the streets involved, they put controls on the heights of the buildings, such that you could get light down to the very, very bottom. So the result is you end up with a very, very distinctive Manhattan landscape. This is London, where everything goes right now. You can build any building you want, it seems to me. So this is the picture I took in central London. Here are a set of towers, and you can see that they're completely clustered. All of them are built in glass, they're all reflecting energy off each other. It's almost like a neighborhood of buildings. The wind between these buildings, you cannot characterize it because it depends completely where the air is coming from, how it makes through the gas of the buildings down to the ground. So what does the geometry do? Well, first of all, it generates shadows. So in a climate like this one in Sao Paulo, it is the management of shadows seems to be the most important thing you can do with regard to design. What else happens when you put geometry into place? Well, the beam of sunshine no longer gets one bounce and then it goes back out again. It actually gets reflected multiple times in the street. So you can see it here. These buildings are reflecting energy off each other. Part of the reason this building here might have a problem trying to control its temperature is not because of the energy coming directly from the sun, but because of energy reflected off another building onto it. And just as it reflects energy on that building there, this energy is reflected over there. Multiple reflection. This means that the beam might experience many, many instances of arrival and reflection in the city street. At night time, what's the other effect? Well, at night time in the city street, what happens is the amount of sky that I can see from the bottom is very, very small. That means that the energy that I emit from the ground here, a lot of it will be absorbed by the building here, the building here. Those buildings have temperature, so they'll emit it back down to the ground again, back down to the ground again. In other words, the effective geometry itself alone will mean that that surface will cool down very, very slowly at night time because of reduced sky view. And finally, as we said, the effective geometry is simply to reduce the convection outside the street, the mixing of those. So that's all about the physical. That's all about the function. So that's about the transport. That's about the heating and cooling systems of buildings. Big thing with regard to climate in cities is where is the waste heat being generated. If the waste heat is at the top of the building, that means it goes into the overlying air. But if it's on the side of the building, it probably goes into the spaces that you and I occupy. Many cities around the world, for the modern buildings, the modern office buildings, they tell them they cannot put their air conditioning units on the side of the building, they must be on the roof. They can't vent the system near ground level where people walk by, they must vent it at the top of the building itself. But in many older structures, that's not possible because there is no air conditioning system, it's central. So we end up with thousands upon thousands of air conditioning systems on the side. Transport also adds heat to the atmosphere, and so does all the various industrial activities. We often refer to this as the anthropogenic heat flux. So the urban climate is partly because of the physical geography, which changes the nature of energy and how it's distributed, but it's also part of the contribution of direct heat out into the atmosphere. This is probably the best known effect of the city. Though sometimes, by the way, it's not always the most important. For some reason, geographers have spent an awful lot of time focused on the urban heat island, whereas the meteorologists have largely focused on air quality issues. So air quality issues are chiefly about air pollution and about wind. But the urban heat island has fundamentally got to do with the energy exchanges. Now, I just want to make it clear that there are many different types of urban heat islands. We tend to see images that say the urban heat island is this or that, but there are different types of urban heat islands, and they're studied differently. This is the most common type of urban heat island. It's been studied for over 200 years. And it's an air temperature heat island, measured in the spaces below the level of buildings. In other words, if you took a weather station that was in the countryside, you put the weather station so that the temperature is measured at about chest height. Well, this is measurements of chest height in the city of London. Okay, so it is below the heights of buildings. That's air temperature urban heat island. Here's the thing. The air temperature heat island is strongest at night time. The strongest at night time when there's no cloud in the sky, when it's very calm. So the nighttime urban heat island is strongest under calm conditions. There's very, very little clouds in the sky, clear skies. That's what we refer to as the canopy level heat island. It's been measured, as I say, for over 200 years. The first person to measured in London himself and his family, basically took temperature measurement for 26 years. They determined that there was a heat island present. Now, he wasn't remotely interested in heat island, right? He was very disturbed that the city had affected his measurements, so he wanted to get rid of them. He thought they were contaminated. That's the nighttime urban heat island. This is what you most often see these days because it can be repeated regularly. It only exists since about the 1970s. That's what's known as a surface urban heat island. The surface urban heat island is detected usually by satellite. So satellites record the thermal signature of the underlying surface. Now, I'd like you to think about what the satellite sees. The satellite is probably about 80, 90 kilometers above us, looks directly below. It most often sees the rooftops of buildings, some of the side of the ground. Now here's the thing, the surface urban heat island is strongest during the daytime. The strongest during the daytime, and it's clearly a function of the different types of land cover. So where you see it reddest here, that's where the landscape is most impermeable, most built up. Whenever you see it blue here, it's where the vegetation is, where there's water. So the satellite picks up the surface urban heat island very well, but it just sees a portion of the surface heat island. If the satellite were in a different position, it would see a different portion of the urban surface, and you'd get back a different surface urban heat island.
Let's say the thermal band.
This is the thermal band of Landsat that's used for this one. This is from NASA, this is New York City. There's Manhattan Island. There is Central Park. The surface urban heat island is a lot more complicated. It's very, very difficult to study simply because it's determined by individual surfaces. And cities are extraordinarily diverse in terms of surfaces. This is somewhat easier to study because the effect of the atmosphere is to simply mix together, integrate all the contributions of the surface. But I want you to remember that the near surface air temperature does not measure the impact of roofs. It measures the impact of the walls and the ground mostly that surround the air inside the street. So there are different types of heat islands. By the way, this matters depending on what you want to fix. So if you want to fix the surface urban heat island, you change the fabric, or you change the surface cover. You add vegetation. If I want to fix the nighttime urban heat island here, I have to think about other ways of doing so. You may remember I spoke before about the issue of risk. I said risk was a combination of hazard. So you might determine that the urban heat island is a hazard. Then it's a question of exposure. In other words, who is exposed? During the daytime, people are at work or are at home. It's where the energy from the sun is most intense. At nighttime, it's when your body's supposed to cool, supposed to relax. Most people are at home. Okay, so that's about exposure. Then there's vulnerability. So ask yourself, who's more vulnerable in these circumstances? Is it the householder? Is it the person out in the street? Is it the person at work? So if I want to manage the urban heat island, I better consider the risk associated with different parts of the city and who occupies it. So this is a lovely summary. This is by Jim Foot. This is for the United States Environmental Protection Agency. Now, if you look at the models they have, ask yourself whether they can be applied directly to somewhere like Sao Paulo. A typical American city has low-lying suburbs. Then it has what they refer to as a central business district. then we're back into a white surface again. In other words, most American cities have a very distinctive design. At night time, you live here. Daytime, you work here. Go back and forth. So what do we see? This is the surface temperature, air temperature during the daytime. Surface temperature, enormous variation of the course of the day. And the reason for this is because each of the individual surfaces is responding differently. So what the satellite is picking up is the response to each of these. So for example, here is a pond park. All of a sudden the surface temperature plummets. Here, for example, the city centre, it sees just the rooftops mostly. It's very hard to see the walls. The temperature shoots up. Sometimes it sits in between streets and you can see the areas that are in shadow. Look at the air temperature. Very little variation over the course of the day. So during the daytime, the real challenge for you is to try and manage the surface temperature. Because that affects you because of the mean radiant temperature. Remember, the temperature of the area surrounding you radiates to your body. At night time, look what happens. There's the air and here's the surface. Is the air temperature usually is the strongest over the course. Right? There's the surface temperature. You can still see the effect of the pond. Remember, the pond is water. Now it appears suddenly as a very, very warm surface at night time. The air temperature, however, shows a general pattern toward the city centre, buildings very close together, out of the edges. So there are different types of heat islands. They respond differently by day and night, and they're measured differently. Remember that the air temperature one is in between the buildings, where that air is turbulent, mixed. It connects together the rooftop with the tree, with the pond, with the adjacent area. That's what happens near the ground. Whereas the surface is based on the tops of trees, tops of the roofs, make the side of a wall that you can see, the area in between. The different types of heat islands. So that's when people talk about mitigating heat islands. Sometimes there's a bit of confusion about how to do it. Clearly, you can mitigate heat islands through some simple strategies. This one in New York I was telling you about. There's a public housing scheme in Brooklyn. Very simple idea, just paint the rooftop white. Now, this is interesting benefits, right? If I paint the rooftop white, that means it absorbs less energy from the sun. That means that the roof is cooler. That means that the air below it, the room below it is also cooler. That means they have less need for air conditioning systems. Which means that they dispose of less waste heat in the environment. So this is a good strategy because it directly affects the surface of the environment. And indirectly affects the canopy level of the environment because it reduces energy use. I'd like you to look at the streets in between, which are covered by trees. I can tell you straight off that the nighttime urban heat island inside this part of the road will actually be quite high. And the reason is because from the street level, the entire sky is obscured. You cannot see the sky, either because of the buildings or because of the trees. So that will affect the surface heat island. It will not affect by very much the canopy level. So you'll see a variety of measures people talk about. This is what they refer to as cool roofs. Another strategy is to put gardens on top of roofs. Another strategy is to have cool paving, in other words, have white paving. Does anybody see a problem with having white paving? Are there any reasons not to do that? So rather than having asphalt which is black, maybe if I had asphalt that was white, that would be an improvement. What do you think? Absolutely right. Now, white surfaces reflect. If I'm on the ground and the ground is reflecting, well, it's going to reflect somewhere. The ground might be cool, but it's cool because it wasted or disposed of its energy onto my body. My body is a very good absorber of energy, which means although I've reduced the temperature of the surface, I've increased the load on myself. The other thing is that, generally speaking, your eye is very responsive to glare. So white surfaces tend to be quite glaring and cause visual impairment. So what works for a roof wouldn't necessarily work for the street. So the thing about cities is they alter every single aspect of weather and climate. This is one of my favorite pictures. It's from a typhoon that was coming in Japan. This poor man was trying to get up the street. See how he's managed mechanically? He has to put his head forward. This guy is standing about a meter away, just looking at him. In other words, over that tiny distance from there to there, can just practically turn in. Right? So this is the thing about cities, extraordinarily diverse. Here's an extraordinary photograph that's taken on the beach in North Carolina. Here is air which is very, very close to being saturated, coming in from the ocean, and it meets a barrier. This is a very, very typical type of building which you see in North America. You also see it in various parts of Europe. Beachfront property is extremely expensive, so what they do is they put tall buildings there. The tall buildings have access to the ocean, they can see everything. But here's what they do. They effectively block everything behind them from the effects of the ocean. In this case, you can see it perfectly because as the air comes off the ocean, it's very, very close to being saturated. It gets slightly displaced by a very, very small amount into the atmosphere, and all of a sudden you get the formation of a cloud. You see the cloud going over the top of the building and then it disappears. In other words, as soon as it sinks again, its temperature rises, and the cloud disappears. So what these two images show us that cities are an incredible variety of microclimates. From the point of view of, say, management from a perspective of the human being, is the microclimate scale issue that's critically important. If I want to examine global climate change, I might think about how the city as a whole affects climate. But if I want to design a city, make effects, it's larger at the scale of the microclimate that I need to make that decision. Okay. Now, I'm going to show you some simple software that can demonstrate to you to what extent the geometry of the city affects important aspects of the climate. And the name of the package is UMAP, stands for Urban Multi-Environment Prediction. UMAP is a product of University of Reading. We're going to take a break in a moment. I just need to make sure, as I said, that I can get the data sets on here so we can demonstrate it. What's happened over the last 20 to 30 years is that our understanding of how urban planners affect the environment has gotten progressively better and better. So people studying the urban environment who are climatologists like myself, meteorologists who might be interested in air quality, architects, urban designers, in other words, lots of different people. All of whom use their own different models to try and understand how cities affect climate or weather. This was an attempt to try and put together all the models into one place that might be applied to something. It's free software. UMAP is a plug-in within QGIS. It allows you to do a series of different things depending on what type of work you're doing. So here's a list of all the applications at our disposal. This one here is called source area footprint. Essentially, what that means is that when I take a measurement in the atmosphere near the surface, within the surface layer, I want to know where it got its information from. In other words, did it come off a grass surface? Did it come off a roof? Did it come off the nearby ocean? Now, there's a way of doing that. It's called footprint analysis. This will allow you to identify the source of the information in the temperature measurement, humidity measurement that you make. This is an urban energy balance model, which is called SUAS. It's a very, very simple model. It takes in information about land cover. And from that information, it will predict what the surface temperature is. These are SUAS, ordinary SUAS advanced. So what they try to do, energy, water, and radiation fluxes. In other words, they try to take everything about the urban environment and to modify it by land cover changes. This one here is CB, and it's about trying to figure out solar energy on individual building envelopes. This one here, which I'm going to use later on, is outdoor thermal comfort. It's based on this model here called Solway. Solway uses individual information about buildings, about footprints. And finally, they have this processor here that estimates just how much heat is being generated by a city. And just based on population, and just based on average energy use. So these are all the models pertaining to UMAP. I'm going to focus on this one here. And what I'm going to do after the break is I'm just going to demonstrate that by showing you on QGIS how it's operational. Now, I tried it, I spent last night with my own computer. My own computer is okay. So if you give too much data set, I'm afraid you just get tired. Then it starts to read, then eventually says that's not finished. So I just need to figure out what size of data set we can run on these machines here. So it's now just 5 to 4 o'clock. So could we meet at 4:30 back here, and then I'll go through and show you this particular package, okay?